Hello and welcome to Lecture 3 of the Oscillations unit of Phys 1201. And we're going to continue our look at simple harmonic oscillations, and in this part in particular, we need to bring energy into our analysis. So the question you might ask yourself is, why do we need energy to think about these oscillators? And I'll point out that a simple harmonic oscillator is a mass on a spring. And as we saw last semester, the force exerted by a spring depends on the amount of stretch or compression of the spring. So this is a force that varies, it's non-uniform, and whenever we have non-uniform forces, we do not have uniformly accelerated motion, and so the approaches to analysis where you use Newton's second law become very difficult as soon as the acceleration is non-uniform. And in particular with spring forces and other forces like that that vary with position of something, in general the approach you want is energy. So let's examine the energy of a simple harmonic oscillator, and we'll talk about the simplest case we can, a horizontal oscillator with no friction, like we were talking about in the last lecture. So the only force doing work is the spring force. There's a normal and a weight, but they're perpendicular to the motion, so they do no work. And so if we define the system as the mass plus the spring, then the only types of energy we're going to have are the kinetic energy of the mass and the spring energy stored in the spring. And now we should think about a suitable choice of initial and final. What we'd really like to do is, we know if we have an oscillator oscillating with an amplitude A, one thing that might be nice to know is we have a v, a speed, a velocity that's constantly varying. Well, if we knew what it was as the object passed through equilibrium, that might help us figure some other things out. So let's go after that. So if we take this as one instant where we know a lot, we know that the position is the amplitude, and we know that at this moment the mass is stationary. And then another instant where we know a lot is as it's passing through equilibrium. There, the position is 0, and the v is whatever the maximum is. And so we're going to have an energy bar chart that looks like this. Initially, it's not moving, it has a lot of spring energy. At the end, the spring is at equilibrium, and so there's no spring energy, and we've got a lot of kinetic energy. So let's use an energy analysis to get the maximum speed in terms of other things. So we know that initially we just have spring potential energy, which as always is a half k, and we would normally write delta x, but we've set up axes so I can just write x squared. And I'm going to call that the initial x, and that equals in the end the kinetic energy, which as always is a half mv squared, and I'll specify that that's the final v. But remember, I set things up so that we are launching this mass from the moment where it's at rest, and so xi is going to be equal to the amplitude of the motion. And similarly, this moment here represents the time when it's going through equilibrium, and that's when the kinetic energy is as big as it can be, and so Vf must be Vmax. And so I can rewrite this. And I have factors of a half on each side, so those are gone, and if I just solve for Vmax, I get this. And that can be useful because the amplitude is easily measured, and we might previously have measured both the mass and the spring constant, and so if we know the amplitude, we can find what the maximum speed ought to be. But it would be useful to have an alternate version of this expression. In particular, the amplitude is usually easy to measure, the mass is usually easy to measure, but the spring constant is not always easy to measure. And what we're going to see is that we can write another expression where we replace this part here with something that's easier to measure. The way we're going to do that is we're going to use our previous observation that we can set up a circular motion that matches the motion of the mass on the spring. What that means is that at any time, the position, or rather the x component of the position of the mass on the spring, is equal to the x component of the position of this thing going around in the circle. But that also means that the x component of the velocity of the mass on the spring, so I'm going to call that Vm for v mass, is equal to the x component of the velocity of the thing undergoing circular motion, which I'll call Vc. So what we have is that xm is always equal to xc, and Vm x component is always equal to Vc x component. We can right away get something very useful out of this. Think about the moment when the mass is passing through x equals 0. And that is the same moment when the thing going around the circle is up here at the top of the circle. And notice that that means at that instant, its velocity is exactly pointing back in the negative x direction. So at that instant, the speed of the mass on the spring is the same as the speed of the thing going in the circle, because their velocity vectors are parallel, and we know they also have the same x components. Well, we already know a way of writing the speed of the thing going around in the circle. We've already seen way back when we looked at circular motion is 2 pi times the radius of the circle divided by the period. And we know that as the mass goes through the x equals 0 position, its speed is Vmax. And so now we know that Vmax is 2 pi r over t, but remember we had to set this up originally so that the radius of the circle is equal to the amplitude of the motion of the oscillator, and so we have 2 pi over t a. And if you compare that with this expression up here, you can see something rather interesting. Just comparing, Vmax here is proportional to A, and the proportionality constant is root k over m. And here, Vmax is proportional to A, and the proportionality constant is 2 pi over t. And so apparently it's true that... So we've actually got a bonus. First of all, we've got an easier way of calculating Vmax from easily measurable quantities, because the amplitude is very easy to measure and the period is also very easy to measure. But second of all, we've got now a way of predicting the period of a mass on a spring if we know its mass and the spring constant.
Let's look at one use that this sort of thing is put to. So one problem in space flight is that astronauts lose muscle mass when they're out of any gravitational field, and so they need to monitor their masses. But of course you can't just step on a bathroom scale when you're in orbit. You need gravity for a bathroom scale to work. So what they actually do is they have a spring and they put themselves on the end of the spring. They're actually sitting in a chair, but let's ignore that so we don't have to worry about the mass of the chair. And so here's the typical sort of thing you would get. So notice that, while I haven't made a nice cosine curve with a max at t equals 0, we can still read off that here this is 2 periods, and it's the difference between that is 4.3 seconds, and so the period is 2.15 seconds. And now we can use this handy little relation we came up with, and we know k, they would take up a spring for which they know the spring constant, and so we can just solve for the mass out of there. So I'm going to speed things up, and you can do the algebra and check yours against mine.
And so we find that our astronaut has a mass of 70 kilograms. And note I did a quick unit check up here. We have one more trick up our sleeves with this circle. Remember, in the last lecture, we already saw, just by thinking about this triangle and how this line here is the position of the oscillator, and so we can do a trigonometry analysis and see that the position of the mass on the spring as a function of time ends up just being r, which is a cos. We can do a similar trick now using the velocity vectors. So just think about these velocity vectors. At the instant drawn, the velocity of the thing going in a circle is like this, and the velocity of the mass on the spring is like this. And if you go through thinking about the angles, you can see that the angle theta is here. So what that shows you is if you think about the length of this line, so just Vm magnitude, it has to be the magnitude of Vc times, and it's the opposite to this angle, so it must be sine of theta. And we showed before that that theta is what this 2 pi and so on up here is. So this is magnitude of Vc, so that we showed was Vmax. There's only one more detail, because note that this is only the magnitude. At the instant shown, you can see that the x component of Vm here is negative. And so what this is showing us is that, in fact, if we graph with these axes what v as a function of t must look like, it must start 0, it must get negative, eventually turn around and go positive, and this is a negative sine function. So overall we have that v of the mass on the spring as a function of t is negative Vmax sine, where we already know how to write Vmax in terms of k, m, and a, or t and a, whichever is more convenient. So here I've rewritten these one above the other so you can see the similarities, and I've chosen one of the possible ways I could have written v. Well, look, we have x, we have v, we might as well get the acceleration, or more specifically the x component of the acceleration. And we know that Newton's second law has to apply. So ma has to be the sum of the forces. The only force in the x direction here is the spring force, and it points back opposite the direction of x, so it's just negative kx by Hooke's law. And so all I need to do is take the x from up here and plug it in. And so I can solve for the acceleration. And if you look at these three expressions, you'll notice sort of an interesting pattern going on with these factors out front.